Hello, it's video number 21. This is June 27th. I want to talk about my particle system and the hovering orbiting particles over nuclei a little bit, how that would work under this system. This is a sheet I printed in 2015. The back of it has my particle system, how repel and attraction are calibrated. That determines how all this works, this calibration. Okay, the idea is that more charge contrast causes more attraction. That attraction can be so that the two photons follow one another around or nearly attach, or it can be so that they attach very strongly. So you've got all different levels of attraction, and sometimes and often there's attachment. Any composite particle, there's attachment involved, and it needs to be strong. The particle needs to be spherical for it to survive in the environment in which there are lots of collisions. When you have anything protruding, it can be knocked off, and something that's strong enough gets into place and attaches, it's more likely to survive. Something lightly attached, not so much. The more spherical the unit is, the better for survival. In this system, there's also repel. And so repel needs to be calibrated, not just attraction. The more strongly charged the particle two photons are, the more they repel. From middle charge on up to the highest charge. When you go below middle charge, you still have positive charge up from the lowest charge and our uncharged photon. But what it does is it causes, it diminishes the attraction rather than actually causing repel when you get down in the lower charged photon. So that's how this is set up, that's how this works. As far as the repelling part of this, it's all calibrated from starting with the basis is the white to white repel is the strongest repel possible. This is depicted or represented by distance of separation. The two whites here are 330 pixels apart. If the photon is 13 pixels, that's 330 pixels apart. I believe I have that correct on here. And that would be 100% repel. Though that number of pixels. The number of pixels isn't important, it's just representative. It's something to express the amount of repel. So you can have a comparison, visualize the comparison when you look at that to what the repel of other photons. The pink to pink repel is like 66% of that 100%. It would be 66 instead of 100%. I think it's 219 pixels there. The red to red is it is less. I'm not going to read the amount. You can see that. Then you have the red orange to red orange, the orange to orange, the yellow orange to yellow orange, the yellow to yellow, the yellow green to yellow green, and green to green. Then green to green, there's no attraction or repel, but you would start from there. I included it on the repel chart. Let me say that the white is the centermost photon inside of a neutron. The pink, the centermost photon inside of a proton. The red, the centermost photon in a positron. The red orange, or let's see, yeah, red orange is the centermost photon in the 43 mass beta electron. The orange is the centermost photon in the 27 mass beta electron. Now those are these are the gamma types. When a positron breaks apart in a PET scan with an colliding into an electron, their two gamma photons repel one another and they go apart. The gamma type are also photons are also disruptive in the environment, more so than say in radioactivity you have alpha particles, which are helium nuclei. They're not disruptive. You have electrons, the beta particles in radioactivity. That's not disruptive. But a gamma photon, a single gamma photon, is pretty disruptive, especially if you had a lot of them. And one, not so much. But if you had a lot of them, it could change things. The makeup of biological organisms, let's say, it could hurt them. But so those are the gamma particles. They're inside those. The electrons themselves are very copacetic in the environment, but they have the repelling surface particles. But when you break them apart and get release the gamma photon, now you've got something that could be a little bit of trouble. They'll get covered over again, but in the meantime, they're causing the environment to respond to its presence. Anyway, the white. Okay, I've already mentioned that. The white to white repel is also on this side of the chart. You got white to pink repel depicted here. You got white to red orange, on up all the way to green, white to green up here. That amount is shown here. Then you have other relationships shown here between other photons that have repel relationships. Now down here you have, in the bottom is the attraction relationships, and it's based from the highest contrast relationship is the white to black. That's the most charge contrast, and they attach very strongly because of that, and that's called 100%. Everything else is a lower percent than 100%. All of these relationships. When you come down to the bottom, it's the black to black. This is the uncharged photons that would exist in the universe before there was a collection that formed. The reason the collection formed, they're completely spherical and uncharged, and they would have a very low amount of attraction. It would be, I think it's 0.5% is the attraction amount compared to the 100% white to black attraction. It's a 0.5% of that. So there's a little bit of attraction, and they would make a giant collection because of that attraction. It'd take a very long time for that collection to form. When you get a little bit of distortion of shape under compression, you would then have a dark blue, which is the lowest charged. It behaves like an uncharged photon, essentially. But when you have those two paired, there is enough charge contrast now that you have a 1% attraction, double that of a black attracting to a black. The blue to blue, there's more charge involved now, a little more positive charge. Now that diminishes the attraction, so that you have a 0.1% attraction amount of the white to black attraction. When you get to the black and blue, you've got a 2%. There's enough charge contrast, you have a 2% attraction force. When you get to blue-green against blue-green, there's zero. They're ambivalent. There's no attraction, no repel. When you get to blue and blue-green, it's zero, no attraction, no repel. Dark blue to blue-green, there's enough charge contrast to be a 1.75 attraction. The black to blue-green is 4% attraction. Green to green, zero, ambivalent, no attraction, no repel. Blue-green to green, zero, no attraction, no repel. Blue to green, 2%. Dark blue to green, 3.5%. Black to green, 10%. Blue-green to yellow-green, 1.5%. Blue to yellow-green, 2.5%. Dark blue to yellow green 6%, black to yellow green 13%, yellow green or blue green to yellow 2%, blue to yellow 5%, dark blue to yellow 12%, black to yellow 28%, blue green to yellow orange 3.5%, blue to yellow orange 8%, dark blue to yellow orange 18%, black to yellow orange 40%, blue green to orange 5%, blue to orange 11%, dark blue to orange 24%, black to orange 52%, blue green to red 6. No, it's red orange 6.5%, blue to red orange 14%, blue dark blue to red orange 30%, black to red orange 64%, blue green to red 8%, blue to red 17%, dark blue to red 36%, black to red 78%, blue green to pink 9.5%, blue to pink 20%, dark blue to pink 42%, black to pink 88%. That's pretty high. That's what's going on inside of a proton with the photons surrounding its pink. 88%. It's not as high as that in a neutron though. Blue green to white 11%, blue to white 23%, dark blue to white 48%, and then black to white 100%. And that's the way this is set up. And then everything is adjusted according to that, what would exist, what composites, what radio particles, what electrons, all of that. Now I'd like to say next that the yellow orange is like the yellow photon in the environment to some extent, and that it's one removed in charge from the yellow. Now the yellow is involved in electric current. It's also involved in visible light. It's one of the 4 photons in visible light. In visible light you have the yellow green, the green, and the blue-green. And they follow one another around in visible light. There's a couple of those that don't have any attraction, but there's believe it or not, there's enough traction. If they line up correctly, they follow one another around. They don't attach, but that's in the book if you want to look for it. As far as now, I don't want to get into all that about light right now, but there's lots of different variations that can happen in light. But as far as the yellow orange, I mainly show it in my system as attaching to a blue, and it's the innermost radio shell. The reason it's now that's stronger photons, it's not a gamma type. It's more like the yellow than the orange, but its repel is strong enough so that but there are only 2 of them on R3 units, so that's why it's located in it. Even though they're stronger repel than a yellow, and they're the yellows being on the surfaces of yellow and yellow green being on the surfaces of all kinds of those radio units. There's only 2 of these, and that's why it's assigned the closest in shell. But I want to say this: there could be a lot more yellow-orange photons in the environment than I've allowed for, which would mean a lot of those more radio units would have those on their surfaces. There are going to be a lot of those on their surfaces anyway. I just haven't really, it just made it more complex to figure that in as well. But it's probably, that's probably the way it really is. And when you have more of those, you might create more categories than just the 6 radio unit shells that I've come up with so far. You might get another. It might make it so there are 7. They might make it so there are 8. I don't know. But if this is the way reality is, and all this really works, then I've come up with enough to get started with this, and it can be refined and improved on. As far as orbiting and hovering particles, in the book, when I was developing this, I've got some different pages at different stages of determining which ones those would be, how they would locate in relation to a nucleus. And if I'm sure I've said this before, but it's the repelling particles on the surfaces of these, how many there are and how strong they are, that determines where they are in the hierarchy of order of shells out from a nucleus. This is what's so much different than, one of the things that's so much different than the standard model is, everything has to have a reason in this. And so your reason is they have repelling surfaces. Their interiors are attracted. Their surface repelling particles are attracted to the uncharged and low charged particles in the nucleus, but their exteriors have enough positive charge that they can't land, that they have enough repel that they have to hover or orbit. And that's why they take up positions in shells out from the nucleus. And different types would have a different shell. So there's a reason for this. They don't just magically hover and orbit out there. They're hovering and orbiting for a reason. And it has to do with repel, surface repel. Okay, here's the collection source again. I think I've showed this before. The different layers inside the collection. The white is in the center, then the pink, then the red, then all the different reds and oranges and yellows and so forth. Then you get out to the uncharged outer particles and low charge, which are just under those. Which have the least distortion. The dark blues would have the least distortion of the positively charged particles. Here's some of those hovering and orbiting particles, electrons and radio particles that I've come up with so far. And those are depicted there on this page. I've had a little uncertainty about whether the first electron I came up with when I did the first book, I came up with an infrared particle that would collide into everything and would be involved in infrared light, what we call infrared light. It's a black surrounded by 6 greens. The more spherical a particle is, the better it does in the environment because it's more spherical. When you have protrusions of any kind, those tend to get knocked off. And something is going to attach in any position that's available. If it's strongly enough to attract it, then it will attach in a way so it can remain there. And that's what determines a lot about whether these particles can survive, and continue or not. But these two are a little questionable, more so the infrared with the greens, because you're not going to have enough of attraction there with 10% so that it's going to be selective to add greens. I mean, it would happen, but it's that as far as the typical infrared particle, I think it's a 15 mass unit. It would pick up some with more charge contrast. If it has enough, if it has the yellow greens, some yellow greens mixed in with it, or blue greens, you're going to have blue greens. They're going to have less charge contrast, but it's going to pick those up too. But when it makes more of a sphere instead of those just protruding, then that helps it to survive as a particle. And so this is a little doubtful. that it would be selective in picking up 6 greens of black like that. That's a little bit doubtful. This one is also a little doubtful, a little bit more. Now it has a stronger attraction though. Whenever you have a 28% attraction between the black and the yellows, the 6 yellows on the black would definitely stay in place. 10%, not so much. The first radio particle I came up with in my first book was the R4. You have a yellow in the center. Let's see if I can find it here. That's this one. A yellow in the center surrounded by with 3 attached yellows. And now the attraction between the blue and the yellow is only 5%. So this is the one that I have come up with that when you fire it into tungsten, if you can get the right frequency going so that this particle is fired from a nucleus by electric current flowing, gets this one headed that way, then when it'll break apart pretty easily because it's only got a 5% attraction force between the yellow and the blue. When it does that, what comes off of that at basically light speed is the X-ray particles, and it's the blue, it's the center blue. And I came up with that hypothesis when I did the first book about that radio particle and about the blue being the X-ray particle. Now what happens is once it slows down after it's done its job in X-rays, it picks up the yellows again, and it returns to being a radio particle in the environment again. And it'll find its way to around the nucleus into its proper shell. But it can also, a blue could also pick up something else, and it could become another radio particle. Yeah, it could pick up, let's say if there were the blue is also the center photon in this R3 unit. So it could become one of those if there's some yellow-orange photons available. So it could go from that to that. And like I said, there might be others. If you start, I've only used the yellow-orange in this one radio unit. So if you start using, depending on how many yellow-orange are available in the environment, if you start attaching them, they're not as apt to wander as singles like the yellow or the yellow green, because they're more strongly attracted because they have more positive charge. So they're gonna be involved, depending on how many of them are available in the environment. They're going to be involved in radio units. And like I said, if it was determined that there were more of these than I've allowed for, then you would have more radio particles because you would have more of those. That would make more types. So let's see what else. Here they are on this page. It was done like 2014. I've showed this before in a video. Down at the bottom of this page, there's a couple of center units depicted of the inside the neutron and proton. Those are what the positrons surround. That's not, they just happen to be in that location here. They don't really concern these layers, these shells. And I didn't have the shells quite right the way I have them now, at least. I have a 15 particle radio unit that it makes up the second shell. I didn't have it that way here. Later I decided that's determined because of the mildness of the repel of the particles on the 15 mass unit. If it has more, say, yellow greens, then it becomes a neutrino electron, and it has to orbit out here, because if it has a lot of yellow greens, then it's going to need to have more distance from the nucleus, because all those repel. And that's what determines all these, just their surface, how many surface particles, how strong they are, how many there are, how strong they are. That determines where they locate in a shell. Their shell locates. So these would have more yellow greens. Out here, if it's an electron, they would have fewer if they're a radio particle, and they'd locate way down here. Here's more of those when I was drawing those. One more thing about this page. Down here in the corner, I drew a beryllium nucleus. And if you look at the table for assigning electrons and radio shell particles, beryllium would only have like, I think it's 500 and some R3 units, and I don't know, 200 or 300 R15 units, and that's it. It wouldn't have any of these electrons. That was just drawn there because it happened to be a nucleus I could squeeze in there for this purpose. To have that complement of orbiting and hovering particles shown there would take a pretty big, pretty large nucleus. So I want to clarify that.